Today, I guess we want to talk about vacuum tubes. Vacuum tubes really are not boat anchor technology because it still turns out that the cheapest way to get power at radio frequencies is to go with a tube amp rather than a solid state amp. You look at the cost of a solid state amplifier versus a tube amplifier. The solid state amplifiers are considerably more complex and considerably more expensive, and so the vacuum tubes are still doing their thing out there. Also, in audio recording, and if anybody out there is a guitar player, electric guitar player, any self-respecting electric guitar player is using an amplifier that uses vacuum tubes because they have a particular sound to them. So they're still very, very much an alive technology. I've been fascinated by them. Well, I grew up with them. At the time, when I grew up, the transistors were just coming out, and a single transistor was far more expensive than a vacuum tube. Back at the time, when I got my license, which was 1968, you could get a receiving tube for $1.50 or $2. If some of you remember Olson Electronics, I grew up in Akron, Ohio, which is where Olson Electronics was based, and so I didn't appreciate that at the time, but tubes were all around me. The whole tube thing starts with the incandescent light bulb, and that goes back to when Edison invented the electric light bulb. And you have to remember that at that time the power grid was on direct current. The alternating current power grid, there was a huge fight between Westinghouse and Edison on which should go, AC or DC. Edison did some things which are pretty horrible to try and dirty the the reputation of AC. But nonetheless, the light bulb runs on both of them, and a light bulb is nothing more than a piece of metal, such as tungsten, heated inside of a vacuum. And it has to be tungsten because it has to be heated to thousands of degrees. Even if you have an old flashlight that uses an incandescent bulb, that little tiny bulb, that filament inside that bulb is at thousands of degrees Fahrenheit. It's hard to believe that. And what happens is that we boil off electrons from the filament. The electrons, of course, orbit around the nuclei of the atoms. And when you heat something, you essentially agitate thermally the atoms. You shake them. And this is happening on anything that's above absolute zero. When you get them up to several thousand degrees, you literally shake the atoms hard enough that you can shake the electrons out of the atom. And what will happen in a light bulb is that they will form a cloud around the filament. Now, they don't go anywhere because once they're boiled out of the filament becomes positively charged, and that attracts them back. So you're boiling them off, some of them are going back, you reach an equilibrium, and a cloud builds up around the filament. And this is called thermionic emission. Thermal and then ion. This is called thermionic emission. It's fundamental to about 99.99% of vacuum tubes. This is how they get the electrons to play with. Now, in Edison's time, they didn't know about the electron. They didn't know about the electron until about 1897. But something happened with Edison's light bulbs when they burned out. And I did some study on this. What they found was when the filament burned out and broke, that there was a smudge produced. I think you can maybe see it here. There was a smudge that always occurred on the positive side of the filament. There was a smudge that formed on the glass from something. They didn't know what it was. So in order to study this, for whatever reason, Edison added another electrode. You can see this little piece of this rectangle here. We now call this the plate, but he stuck that inside the tube, maybe thinking that the particles would go to it or something. But the result was that he discovered first that if he applied a potential difference of voltage between the filament and that little metal plate, that current would flow. And that was remarkable. That was absolutely remarkable because no one had ever known that you could get electricity to flow through something that wasn't a conductor. I mean, the vacuum we're talking about here. The vacuum, nothingness. Further, he discovered that the current would only flow one way. The plate had to be positive in order for this flow to occur. If he made the plate negative with respect to the filament, there was no current flow. That was fascinating, but not necessarily useful to Edison. You remember, Edison's an inventor. But he noticed that the current did depend very heavily on the current that was flowing in the filament, and he thought that might be useful. So he patented it, okay? And this became known as the Edison effect. Now we know, in 1897, J.J. Thomson discovered the electron. And we now know that what was going on was that electrons were being boiled out of the filament here. And of course, if the plate was positive, opposites attract, so the electrons would flow to the plate, flow around the circuit, back to the filament, and you'd have this current flow through the vacuum, through the battery, and back. There's another battery here that's just shown to heat up the filament. But if you put negative on the plate, you'd push the electrons back. None of them could come off of the plate because it wasn't heated, and so there would be no flow if the plate were negative. So we had a device that was needing it needed to solve a solution. Okay, we had the solution before we had the problem, and he had discovered the diode. Now it didn't take long to figure out what to do with it. They found out that this device could be used in the detection of radio waves. This was during the spark era. Back in that period, they used something called coherers. That would be a fascinating thing to talk about. I'd like to make one. But the tube, the diode, was a good radio detector. Not so much that it was more sensitive, but it was more reliable. The other electromechanical things that they were using for detecting radio waves turned out to be temperamental, persnickety, and somewhat unreliable. But when they got the diode, it became very, very reliable. The other thing, and I'm just sort of guessing here, is that as the power grid went to alternating current, ultimately George Westinghouse won, and it was decided that the power distribution system in the U.S. was going to be based on alternating current, not direct current. Well, that means there were things in industry, such as electroplating. If you want to copper plate things or silver plate things, they need direct current. And so there was a need on a large scale to convert the alternating current that was being distributed by the grid to direct current that they could use. Also, everybody here who is a ham knows that you have to have a power supply for your radio. Invariably, you need direct current for all those electronic circuits, and the diode was the perfect thing for converting the alternating current to direct current, because the current flows only in one direction. So it immediately found a use. And when something finds a use, what you try to do is you got to make a better one. You know, how do you make a better mousetrap, right? And there were several things you could do. Ultimately, you wanted it to be able to handle more voltage, and you wanted it to be able to handle more current. So one way to increase the emission was to add chemicals to the filament. Now, some of you, I don't know if anybody out there recognizes what this is a photo of here, but this is the photo of an interior of a 5U4 rectifier tube, okay? And I have the techniques here in my shop. I can take the glass apart and take tubes apart and pick them apart so you can get a nice picture of them. But in this photo, you can see that the plate is now actually a rectangular tube. So one thing you could do is put the filament inside the plate. I mean, Edison just had this piece of metal and then you had the filament. But it makes more sense to put the cathode inside and the plate around it. Then the electrons can come out in all directions. It doesn't have to be round. Here they have a couple of pieces of metal. If you look at how fascinating how they made these, a couple of pieces of metal with a crimp in them, and then they staple them together or crimp them together. You can actually see the crimps here. And then you got to look close. The filament is actually a flat piece of heating material like nichrome. You can see this flat strip right here that goes inside up to the top and then back down. And then that is coated with a mixture of rare earth elements which give off electrons at much lower temperatures than white hot. So if you look at a 5U4, Rangers, a Viking Ranger has a 5U4. I mean, just about every transmitter out there that's a boat anchor's probably got a 5R4 or a 5U4 in there. You look at that baby, you'll see, if you look at the top, look down on it, you'll see this orange spot, orange to red spot, where the filament has been heated up. And you can't see it here, but it is coated inside. And so you can chemically coat the filament. You can mix chemicals with the filament. So in tubes like the 811, which is used in amateur amps, and the 3500Z, the 813, bunch of them, they mix thorium with the tungsten, because tungsten doesn't emit electrons very well. So they mix thorium with it. It's called thoriated tungsten, and then it becomes a very good emitter, and they use that in them instead. In this case, they put the thorium compound on the outside of the filament. Also, you can increase the size of the plate. I mean, these things here are, you know, like 2 or 3 inches long. And one of the things they started doing immediately was you can stick several units inside one glass envelope. There are some tubes out there where they got 3 or 4 active tubes inside the same glass envelope, okay? But make the plate bigger. It has to be able to handle heat, because the electrons, when they come out and they smack into that plate, they generate heat. So you got to have a way of dissipating that heat. And these places where it's stapled together here, that isn't just to hold it together. The heat is conducted to that, and then it's radiated out through the glass. So part of that is to help cool the entire thing down. And another thing that happened, very important, was the invention of the indirectly heated cathode. And this is a 12AX4 tube. And in this case, the plate, you can see here, is 2 sheets of metal that have a semicircular bump in them stapled together. And that forms a tube. So they make a tube by stapling these together. And then inside it, it's hard to see here, you can see a metal tube. Right here at the very, very top, sticking out, you can see a little metal tube. What you can't see is that inside the plate, that metal tube is coated with a white compound. And that white compound gives off electrons when you heat that metal tube to orange or red heat. And you can actually see folded inside the cathode, folded inside of it, you can see the white wire there. That is the filament. that little white twist you see there, that's the filament. And that white is not plastic, that's ceramic. Remember, this thing's going to get red hot, so you got to somehow coat a wire with a ceramic compound and then wrap it up and shove it inside a little tube that's maybe 3/16 of an inch in diameter. The technology here is just amazing. And this greatly lessens the energy needed to heat up the cathode. You don't have to have anywhere near as much energy to heat up the cathode. It makes it a lot more efficient. All right. And some tubes have a directly heated filament. This one has got a directly heated cathode. This is an indirectly heated cathode. Okay. The filament now is called a heater rather than a filament. And another problem, which is really amazing, is I've learned over the years as a bagpiper, I play the Northumbrian bagpipes and the Irish Uilleann pipes, is that plumbing systems, bagpipes, and at MIT I learned that vacuum systems all have one thing in common, and that is they all leak. They're all going to leak one time or another. No matter how you make it, you're going to have air leaking in where the wires come through at the base of the glass. And so you have to have a method of maintaining the vacuum inside the tube. Now, there are various ways of doing it, but for the smaller tubes, which are called receiving tubes, and the smaller transmitting tubes, this is called gettering the tube. It's called gettering the tube, getting the air out of the tube and keeping it out of the tube. And what's done, for instance, in this 5U4 is when they build the tube, they put this little tray here, this little circular tray. And if I go back to here, you can see that little tray right there. Right now it's empty, but they take that little tray and they fill it with a chemical compound, sometimes barium oxide and other things, which has a voracious appetite for oxygen atoms. If an oxygen atom encounters metallic barium, it immediately forms an oxide. And what they will do is, after the tube is put together, and after they've sucked all the air out of it as much as they can, they will hit this with an induction field. In other words, this becomes the secondary of a transformer. They'll bring a primary of a transformer near this getter, and they will boil that getter material off of that little tray onto the glass, and it forms this silvery area that looks like this. And from then on, any oxygen atoms that are going in around the tube, if they encounter that, and of course they will after a while, are immediately absorbed and taken out of the tube. It is very common. I knew this as a kid. My dad thought this. He thought this was a burned out tube. Okay? He says, oh, that tube is burned out. No, that is a perfectly fine tube. That is perfectly fine. If that area looks smoky white, then the tube has lost its vacuum and it's no good. Okay? Now, in transmitting tubes, there are other ways to take care of the vacuum, but I don't need to go into it now. The point I want to get off is virtually every tube has got this silver area on it that you'll find. Sometimes it's down at the base, sometimes it's on the top, on the side. That tube is perfectly fine. It's perfectly fine. Don't throw it out, don't break it, it's perfectly fine. Okay? Now, in the early 1900s, a man named DeForest made a discovery that completely changed electron. Actually, his discovery started what we now call modern electronics. Modern electronics began with the invention of the triode. Now the transistor and the FET have replaced the triode. But what he did was, if we take a look at this picture here, this is an 811A. I'm sure some of you have got amplifiers out there with 811As in them. It's a great tube, and they still make them. Here, the gray area is the plate, right there. The cathode is a filament that is shaped like an M. Now you can barely see it here. You can see this lead coming in, and you can see a wire there connected to it. That goes up to the top of the tube through a spring, comes back down here, underneath here, goes back up to the top of the tube on a spring, and comes back down and comes out here. And you'll actually see those springs at the top of the tube. And that's because when you heat up a metal, it expands, and you can't have that filament going slack. So when you turn on the filament voltage and the filament heats up, the springs pull on it and keep those wires tight. So the cathode is this M-shaped thing, which is mostly inside, but the important piece is this grid of wires which has been added to it. They put 2 posts on each side, and then in elliptical fashion they wrap this wire around it and around it and around it all the way up to the top of the tube. Look at the precision that has to be used to make that. And you can't have that wire shorting to the filament, and it can't short to the plate, though in some cases it does, and when that happens, really bad things happen. But when DeForest did this in his first crude tube, his first grid was just a zigzag piece of wire. It was just a zigzag piece of wire that looked like a hamburger spittle that you turned hamburgers over with. And what he did, he found that if you put a negative voltage on that grid, it could repel the electrons coming from the filament and reduce the current going out here to the plate. That by changing the voltage on that grid, he could control the current flowing between the filament or cathode and the plate. As a matter of fact, if you made it negative enough, you could shut the current completely off, totally off. And the amazing thing here is that because in most cases, except in a few specialty cases, the voltage on the grid is negative, no current can flow from the grid back to the cathode. Now in transmitting tubes, there can be grid current, but in most other cases, there is no flow, which means that if you hooked your antenna up to this grid, you could control the current flowing to the plate without drawing any current whatsoever from the antenna. It would not load the antenna at all. And if you hooked the plate to a resistor, you would find that if you varied the voltage on the grid, for instance, by 1/100th of a volt, you might find that on the output you got 100 times the voltage variation, or a whole 1/10 of a volt. The triode can amplify. You can put a very small signal on these turns of wire. On these turns of wire. Got to grab the right thing here. There we go. You put a very tiny signal on these turns of wire, and you can get a much larger signal in the output circuit. Sometimes hundreds of times larger. Because the triode can amplify, this is what initiated the entire field of electronics. If you grab an electronics book from the 40s or the 50s, it's a book about vacuum tubes. It's all about vacuum tubes. Nowadays, electronics is about transistors. If it's about computer chips are transistors. A triode can amplify a signal. You can turn it off and turn it on. You can make the grid really negative and shut it off. Make the grid 0 volts, it comes on. And most importantly, to us hams anyway, is that if it can amplify, you can take the output of the tube, feed it back to the input, and if you do it in phase, the amplifier will provide its own input. This is like holding a microphone in a PA system up to the speaker. It'll oscillate. And you can generate oscillations at virtually any frequency. And in particular, up until this time, it was impossible to generate a continuously varying radio frequency wave. All of them had to be damped. They would die down over and over again. This was the spark era. This was the introduction of CW, continuous wave. Instead of having a sequence of damped oscillations that would die down over and over again because a spark would produce them, you could have a continuous oscillation, and that ushered in the modern field of radio and in particular electronics. And that was, by the way, patented. If you wanted to use a vacuum tube to generate a CW signal, you had to pay somebody patent rights to do it. And patents were ferociously defended back then. Okay? Now, here's the tube I'm sure a lot of you have seen. This is a 3500Z. I bought this at a ham fest. It broke my heart when I saw these sitting in a box. I don't know how they got busted or how they got overloaded, but somebody really did a job on these. They really did. But one of them I kept, the other one I broke open. And in this case, the plate is actually made out of pleated metal, round and round and round, because it has to be able to dissipate about 500 watts of heat, because when those electrons smack into that plate, they heat it. So here's the plate of the tube. It's normally welded onto the cap. But in this case, they had overheated the tube to the point where the plate welds melted and the plate fell off and was just rolling around inside the tube. Somebody really did a number on this baby, okay? What's really cool, there's the plate, here's the envelope, there, right there, that is the grid. The grid in a 3500Z is not a spiral of wire, it's a bird cage. It's a little tiny bird cage that's perhaps a quarter of an inch in diameter. With the filament, you can just barely see the filament inside there, okay? Needless to say, if that filament should short to the grid cage, bad things happen. These things have to be handled carefully and operated carefully so that you don't overheat them and do bad things. The worst thing you can do on a power tube is to give it too much grid current. This is a tube that is run with grid current. The grid goes positive. It is possible for enough electrons to hit that grid, if it goes positive, that you can melt the structure. And if it melts and touches the cathode, boom. If it melts at all, the tube's ruined. But if it touches the cathode, there's a short in the filament circuit. That's really bad. And this one tube is with proper power supply. Two of these, if operated properly, could give you legal maximum, 1500 PEP output, which is the amateur limit. So two of these could give you the legal limit in ham radio. Now, a far more common tube is the 12AX7. This is in virtually every guitar tube amp out there. And if you've got a classic radio, like a Viking Ranger, the speech amplifier in most tube transceivers and transmitters is a 12AX7, which means if you're operating your vintage rig on sideband, the signal from your microphone is going right in to this tube. Okay, it's a 9-pin tube. You can see about how big it is. It's I don't know, 3/4 of an inch in diameter. There are 2 triodes inside of it. Again, it's very common to have 2 tubes or 3 tubes inside of a single element. It's what we call a high gain tube. There's a whole family of these: 12AT7, AU7, AV7, AX7, blah, 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 blah. They're all the same. They all have the same pinout. They all have the same filament requirements. The difference is how many turns they put on that grid. And ultimately, the ones that wound up being used were the 12AX7, the AU7, and the AT7. One of these triodes has a voltage gain of as much as 70, which means if you put an alternating voltage on the grid, in the output, the voltage change in the output will be 70 times larger. And if you run the signal from one triode out of that into the next triode, 70 times 70 is 4,900. Call that 5,000. It means that this tube can amplify an audio signal, the voltage of the signal, by as much as 5,000. So if your microphone puts out 1,000th of a volt of audio, which is reasonable, you run it through a couple of these and you'll have 5,000 times that coming out, or 5 volts coming out in the output. And if you've got a Ranger, I have a Ranger, Viking Ranger. A Viking Ranger has one of these tubes as the input tube. It runs it through one triode, then the next, amplifying it by about 5,000 times between the mic jack and the grid of the modulator driver tube. You find these in audio amps, guitar amplifiers, audiophile amplifiers, microphone preamplifiers, speech amplifiers. They're all over the place. Now here's the part I like. I took this tube, and in my metal shop I can do remarkably precise work, and I cut open one of the triodes and folded back the metal. Here you can see this is where I've cut it off. There's the cut edge. And I folded the other side back so you could see what's inside one of these babies. And if you do a super close-up of it, this is what you see. It bothers me that people call equipment boat anchors, because a boat anchor is something that's completely worthless except to hold a boat down. Folks, this stuff was being made in the 1940s and 50s. Can you imagine the machinery that was used to do this? This is beautiful because you can see the cathode in the middle is this tube right there. The white coating, this is the top of the triode. Here's the white coating that gives off the electrons. Inside this tube is the heater. And then on each side, we've got these posts which hold the grid. You can see how close the grid is to the cathode. That cathode, this pipe here, right here, that's a 1/16 of an inch right there. So this is unbelievably close, and they could crank these things out by the hundreds of thousands and millions, And back in 1968, you could buy one of these for $1.50. Nowadays, you can buy one for about 15 bucks at the local music store. They're still made. They are still used. Good things don't go away. They keep on using them. Okay. So the triode comes in all kinds of shapes and sizes, but the 12AX7 is one of the most popular ones. As far as schematic symbols, this is how we diagram vacuum tubes. A circle is drawn to represent the envelope. There's a circle drawn here. The plate is just a straight line. Of course, it's actually a cylinder or a rectangular cylinder or whatever. The cathode is usually a round tube, but here it's just shown as like a hangman's a piece. The filament is shown as just a wire. If this were a directly heated diode, for instance, the cathode symbol would be missing. And when you talk about diode, triode, tetrode, the heater is not counted as an active element. So the triode has 1, 2, 3 elements. We don't count the heater as an active element unless it's a directly heated cathode. The pentode, we'll be talking about these. The pentode has 1, 2, 3, 4, 5. Pent means 5. Tet means 4, and so forth. So if you look at the schematic diagram for your vintage rigs, you're going to see these things all over the place. Now, triode has got a problem. If you go back and look at the interior here, the pipe in the middle is a conductor, that's the cathode. And the grid structure is another piece of metal that's a conductor. And they are separated by the vacuum, which is an insulator. And that means that they are two elements separated by an insulator. This is a capacitor. This is a capacitor. The grid and the cathode form a capacitor. The cathode and the plate form a capacitor. These are called the inter-electrode capacitances. But the one that's critical is the one between the plate, which is the output, and the grid. I think all of you should know that a capacitor will pass alternating current. At audio frequencies, this capacitance is very small. It's not a problem. But when you get up to radio frequencies, you will find that enough RF from the output can unintentionally get fed back through that capacitance to the input that it oscillates even though you don't want it to oscillate. This is called a parasitic oscillation. Solid state devices will do this too. But in the triode, this was particularly bad. And if this happens in a power amplifier, you can get an oscillator here, and it doesn't necessarily oscillate on the frequency you have it tuned to. It can go off on some other frequency. I once had an 813 connected as a triode do this, and it burned up part of the plate circuit because 500 watts didn't have any place to go, and it just burned up some of the wiring and the coils that I had there. And this is undesired feedback, and something has to be done to deal with it. Now, some of you might have heard of neutralization. My Ameritron amplifier is a 572, an AL572. It has 4 triodes in it, 4, and it's neutralized. And what that means is they intentionally feed some of the output back to the input, but in the wrong phase, out of phase. When you neutralize an amplifier, you take some of the output and feed it back to the input out of phase. And if you adjust the amount of that, it can just exactly cancel this positive feedback, and then the system is stable and it won't oscillate. So triodes, even triodes like the 3500Z, which are operated in ground and grid, they're usually neutralized as well as part of good engineering practice. Problem is, if you try and do this neutralization in a receiver, trying to use triodes to amplify the signal coming in from the antenna, you typically have a triode feeding another triode, feeding another triode, feeding another one. And this situation is they start all feeding back with each other, and it's just a mess. If you try to neutralize receive triodes in the early 1920s receivers and stuff, it was a nightmare. They did invent one called a Tetrode receiver, but it was still, really unstable. Really unstable. Something had to be done to eliminate this undesired feedback. And the solution to that was to add another grid. So here's the schematic diagram. This is not to scale. These schematic diagrams are not to scale. This grid over on the triode should be drawn almost touching that cathode. And this grid should be drawn almost touching that cathode, and the screen grid, which is this is called, should be almost touching that. The plate is much farther away. So the schematic symbols don't show to scale what's inside the tube. They're just there so you can see how things are hooked up. Now what does this do? You put this thing here and you put a positive voltage on it, typically several hundred volts. 400 volts, 200 volts, 600 volts, it depends on the particular situation. And that voltage on that screen grid must be absolutely constant. It has to be bypassed to ground, no signal appearing on that screen grid. It has to be absolutely constant direct current. And what this does, it does two things. It is an electrostatic shield between the grid and the plate. I mean, in the extreme case, you could just put a piece of straight metal here, a grid with an infinite number of wires. Well, obviously, if you got a capacitor with two plates and you put metal in between them, it can't function as a capacitor anymore. Well, in this case, you don't put a complete metal plate, you put a grid. And if you put enough turns on it, typically the same number of turns as you have on the control grid, it functions as an electrostatic shield, and it reduces that capacitance and it eliminates the feedback. And this is the Tetrode. And it does something else too. Because it's really close to the cathode and it's really positive, in some tubes it's at the same voltage as the plate, it literally sucks the electrons right off of the cathode. It produces this huge force that just rips those electrons away from the cathode. Boom, they're gone. The grid, the control grid, can still control them, but pretty much it whips them away and they zip off. Some of them hit it, so some of them do hit that grid, but most of them go through it and eventually hit the plate. The result, it increases the voltage gain of the tube. So instead of amplifying 70 times like the 12AX7 did, it might amplify 400 times in one tube. A voltage gain of 400 times in one tube. It's just phenomenal. And without the feedback problem. So the Tetrode was a huge advance. But wait, If you order now, I'll give you a Ginsu knife, and also you can buy 2 for the price of 1. No, there's a problem. There's a problem. What most hams don't know is that the voltage present on the plate of a tube, whether it's a triode or a pentode we'll get to, or a tetrode, when it's amplifying a signal is not constant. This is the most common misconception. If you go into my Ranger, which has a 6146, and you put a voltmeter and you properly isolate the voltmeter, you don't do this with the thing transmitting. If you do this with the things transmitting, you have to use an RF choke and couple the voltmeter correctly to the plate of the tube, okay? The voltmeter will read 500 volts. It shows 500 volts. You look at the voltmeter, it just shows a constant 500 volts. What you don't know is that if you couple a properly coupled oscilloscope to that tube that can handle a couple of thousand volts on the input. Don't try this with a regular scope, you'll blow your scope out. But if you connect an oscilloscope that can measure AC voltages up to several thousand volts, what you'll see on that final tube is the voltage going up to 1,000 volts, down to almost 0 volts, up to 1,000 volts, up and down from 0 to 1,000 volts at the radio frequency that's being amplified. So sometimes during the cycle, the plate has a very low voltage, and sometimes the plate is lower in voltage than the screen. So for instance, in my 6146 amplifier you can see on the web, the screen voltage is kept at about 180 volts. And the plate voltage is jumping up and down, like I say, between 0 and 1,000 volts. So sometimes the plate is at 1,000 volts and the screen's at 180. Other times the plate's at 0 volts almost and the screen is still at 180. And that causes a problem. Because when the electrons flow from the cathode to the plate, they're actually going tens of thousands of miles an hour. Okay? Tens of thousands of miles an hour. And when they slam into that plate, they can cause electrons to splash out of the plate. Imagine taking a bucket of water and then shooting a fire hose into it. If you keep the fire hose down, you just splash some water around. But if you take a full 3-gallon bucket of water and you hit it with a stream of water from a fire hose, you can empty the bucket. You can empty the water out of the bucket by splashing it out of the bucket. This is exactly what happens when the electrons go from the cathode and smack into the plate. If the plate voltage is more than about 20 volts, they're going more than fast enough to make this happen. And it's called secondary emission. It's called secondary emission. Okay? And in a triode, if the electrons are splashed out, they just fall back into the plate. Imagine a bucket filled with water, but the sides of the bucket are very deep. So that if you hit that with a hose, you splash the water up, but it stays inside the bucket and it just falls back down into the bottom. This is what happens in a triode. But in a tetrode, when the plate voltage swings below the screen voltage, those electrons are attracted to the screen grid, travel to the screen grid, and are collected. And you can have an electron hitting the plate and knocking out 3 electrons which are lost to the screen grid, which means you have less current flowing out of the plate. There's actually a region here, this is weird, where if you increase the plate voltage in a static situation, the plate current goes down rather than going up. It goes down. You increase the plate voltage and the current goes down, and then it starts to go back up again. That's actually called negative resistance. It's fascinating. I've studied it, okay? What this does is it causes severe distortion and it limits the power output. If you try to make the voltage on the plate go too big, you start losing electrons to the screen grid and you can't get any more power out of it. And they discovered this very quickly. Very quickly, they found out that this was happening. So what'd they do? Well, they added a third grid near the plate. Now, if I drew this to scale, these two grids would be way down here, and this suppressor grid, as it's called, is way up here near the plate. That is put at ground potential at 0 volts. It doesn't have to have very many turns. I'm going to show you the inside of a pentode here. You'll see how it's made. And what this does is it creates a strong field that will repel any secondary electrons back into the plate, eliminating the lost electrons and allowing you to run the plate swing as big as you want. And the result is you can get huge voltage gains up to 400. You've all got radios out there. Drake has 6BZ6s in it. You see 6AU6s, 12BA6s. These are all pentodes. And the pentode really is sort of the culmination of a vacuum tube technology. For audio lovers out there, the EL34 is a high fidelity audio power tube that is truly a pentode. Okay? Here's what it looks like inside. So there's your where's my little pointer here? And here's, you can see the cathode, which is white. You can see the screen grid and the control grid, and then there's this other wire here. That's the suppressor grid. Okay, this is an audio power tube. Okay, and your 6146s, your 813s, these are all pentodes. Okay, so I can finish up here pretty quick. Okay, all kinds of envelopes can be used for tubes. They can be glass, they can be metal, they can be ceramic, and there are some tubes like the 6L6 which can be glass or metal. The glass can replace the metal, but not the other way around. All right, and metals were common in World War II. They were eventually replaced with glass because it's cheaper. Okay. Numbering scheme. This I bet you don't know, Howard. I'm going to bet you don't know this, and I bet you a lot of you don't know this. Okay. At least the last one. The first number in the tube is the filament voltage. 12 volts for a 12AU, 12 volts. A 6AQ5 is 6 volts. 6 volts. A 3V4 is 3 volts. A 1U4 is 1 volt, and so forth. The last number, though, is the interesting thing. This is the number of active elements in the tube. So a 12AU7, the 7 means 1, 2, 3, 4, 5, 6, and then in this one you do count the heater because it is an active element, 7 elements. A 6AL5, 1, 2, 3, 4, 5. So there is a rhyme or reason. Testing tubes. The best way, if you're a vintage ham, you should try to get a known good tube for every one that's in your radios. Okay, you don't have to have 6 particular tubes, but the best way to test a tube is to replace it with a known good tube. For transmitting tubes, you really cannot use a tube tester to check them. You have to replace it with a known good tube. That's the only way you can really do transmitting tubes. Tube testers, if you can get hold of a dynamic tester, get it. Most of the tube testers out there aren't very accurate. They only test whether it can put out electrons, and they're not very reliable. Okay, they're not very reliable, but they can help you out. Much better is a Hickok. It actually uses the tube to amplify They are far more accurate, but still the best way is to replace it with a known good tube. Okay? And I think that's it. Okay?